In 1999, all signs pointed to the Mars Climate Orbiter making history. It was set to be humanity's first interplanetary weather satellite, tasked with studying Mars's atmosphere and mapping its surface water in unprecedented detail. 4 years of planning and 10 months of space travel seemed about to pay off. But on 9/23, just as the probe began entering Mars's orbit, contact was lost. NASA's control center was instantly plunged into confusion and frustration. A $300 million project, including equipment, data, and technical work, vanished in an instant. What had gone so terribly wrong? An investigation began, and on 11/11 that year, the Mars Climate Orbiter Inquiry Board revealed the shocking truth. The error was in the units of measurement. NASA used the metric system for calculations, while a contractor used imperial units. The result? The spacecraft's trajectory was wrong, likely causing it to disintegrate in Mars's atmosphere. This incident taught us, modern science relies on teamwork and standardization. Without absolute measurement standards, chaos reigns and orbiters fall. But think, units like meters, kilos, or hours stem from human experience. A meter was once defined by a platinum rod's length. A kilo equals the mass of 1 liter of water, and an hour? It's an arbitrary division of an Earth day. But off Earth, in the cosmos, these references make no sense. There's no platinum rod, water liters, or Earth days out there. So how would an alien measure their world? How can we create a truly universal system of measurement? These questions intrigued German physicist Max Planck in the late 19th century. A professor at Berlin's Friedrich Wilhelm University, Planck was a theoretical physics giant and Nobel laureate. He believed nature's laws could be studied at fundamental discrete scales using the universe's own constants. While a planet's rotation may vary and gravity differs on each celestial body, some things never change. The speed of light, for example, is constant. The gravitational constant is too. What if we used these immutable constants to create a truly universal measurement system? That's exactly what Planck did. In 1899, he introduced the world to Planck units, based on fundamental constants like light speed and gravity. The Planck length, for instance, is just 1.6 times 10 to the minus 35 meters, an unimaginably tiny fraction of a millimeter. Planck time, derived from this length and light speed, is only 5.4 times 10 to the minus 44 seconds. To put it in perspective, there are more Planck time units in 1 second than seconds in the entire universe's history. While this may seem too minuscule for us to grasp, these scales are crucial for scientists deciphering the universe's greatest mysteries. They've helped us, for example, to understand space and time in their most fundamental form. This directly relates to a theory once deemed absurd, but now widely accepted. It posits that the entire universe emerged about 13.8 billion years ago from a tiny particle that expanded incredibly fast. The famous Big Bang. Cosmologists are pushing knowledge boundaries further back in time, exploring the universe's earliest moments. Impressively, physics advances let them reconstruct events just after the Big Bang, once thought impossible. At this extreme frontier of cosmology, Max Planck's fundamental units come into play. scientists exploring the universe at one Planck time and length are venturing into the Planck era. This tiny instant defies intuition, representing physics' wild frontier where even established laws fail. In this compressed, dense, chaotic realm, everything we know unravels, shatters, and mind-bending possibilities emerge. Before discussing how these laws break down, we must understand what exactly is breaking. In the late 17th century, legendary English physicist Isaac Newton published his masterpiece, Principia Mathematica. This work not only presented his famous three laws of motion, but also formulated the law of universal gravitation. The idea was brilliantly simple. Two bodies attract with a force proportional to their masses and inversely proportional to the square of their distance. This elegant formula became a pillar of classical mechanics, explaining planetary, lunar, and cometary motions for over 2 centuries. But then, over 200 years later, a restless young man with a tough life enters the scene, spending his days bored at a patent office in Bern, Switzerland. His name, Albert Einstein. Working there was never his dream. After a rocky school life and failed teaching job attempts, he took the position just to pay bills, but his mind stayed fixed on physics. While stamping papers, he'd sketch tiny solar systems with orbiting planets in the corners. This was his escape. Einstein obsessed over the big questions physics hadn't yet answered. Then in 1905, his miracle year, he published a series of groundbreaking papers. One introduced a new theory, scrapping part of classical mechanics, the special theory of relativity. In this theory, Einstein explained how time and space behave at near-light speeds. Better yet, his work reached Max Planck, who immediately recognized its value. With Planck's support, Einstein left patents to dive into theoretical physics. But he didn't stop there. He spent the next decade trying to unite gravity with his revolutionary space-time ideas. It wasn't easy, as Newton's gravity worked too well to simply discard. Still, Einstein persisted, and in 1915 presented another bold theory, general relativity. This theory changed everything. It proposed that gravity wasn't a pulling force, but the result of space-time curvature. In other words, massive objects like planets and stars warp the space around them. The greater the mass, the greater the curvature. Imagine placing a lead ball on a trampoline. Now toss a marble near it. The marble will orbit the lead ball, following the trampoline's curve. This example has limits, but it's practical for understanding. Amazingly, experiments confirmed this theory, like Mercury's orbit anomalies. Einstein's gravity view revolutionized science, ushering in modern physics. He proposed massive objects warp space-time, giving scientists powerful tools. By solving general relativity equations, Belgian priest and physicist Georges Lemaitre imagined an expanding universe from a hot, dense state. He thus planted the seed of what we now know as the Big Bang theory. But even Einstein's elegant equations have their limits. In extreme regions like black holes, where masses of billions of suns compress into a point, space-time warps so much that light can't escape. In this scenario, Einstein's mathematics simply breaks down. Physics can discuss infinite densities or infinitely small points, but when infinity appears, we know something's amiss. Our equations stop working, and this is more than just a technical detail. It's a valuable clue, as the singularity in a black hole, that point of infinite density where physics breaks, mirrors the universe's state during the mysterious Planck era. For a brief instant, all the universe's mass and energy was compressed into something 100 billion times smaller than a single proton. General relativity helps us grasp the universe at large scales, but it fails when applied to this primordial moment. To uncover what happened in time's first moments, scientists must turn to another theory. Today, when you power up your computer or unlock your phone, you're engaging millions of tiny transistors acting as switches, on or off, zeros and ones. These enable the device to execute commands, launch apps, play videos, and do much more. These silicon chip transistors have been shrinking steadily over the decades. Today, some are just 5 nanometers, about 10 silicon atoms lined up. This miniaturization has made our devices incredibly powerful, but there's a size limit. We're now starting to hit that limit. When components get this tiny, strange things start happening. For instance, electrons can randomly jump between atoms, as if through invisible walls. This can corrupt data and disrupt computer operations. These effects stem from quantum mechanics, where classical rules don't apply. Rather than fight it, science boldly chose to use these quirks to our advantage. Thus, quantum computers emerge. Instead of silicon transistors, they encode info in subatomic particles with an almost magical ability. They can be in 2 states at once. It's like a switch on and off simultaneously until observed. Remember Schrödinger's cat, alive and dead at once until we open the box? Well, quantum bits or qubits work similarly. With this multi-state ability, quantum computers can solve incredibly complex problems impossible for traditional supercomputers. This revolution is just beginning, but relies on quantum mechanics, a century-old field that still seems futuristic. The physics of the tiny may seem detached from our daily life, but this invisible realm might hold the key to cosmic mysteries, including the universe's birth. In the late 1800s, as Max Planck pondered nature's smallest scales, his German peers were fixated on understanding matter's behavior at microscopic levels. Then, a groundbreaking idea emerged: Energy might not flow continuously as thought, but in tiny discrete packets, almost like grains of energy. This notion seemed absurd, especially for light. After all, light had always behaved as a wave. It reflects, refracts, spreads, and even interferes with itself, just like ocean waves. But in some cases, light seemed to act as if made of particles. These invisible, mysterious particles were dubbed photons. The double-slit experiment shook our understanding the most. Light through two slits creates a wave-like pattern on a wall, with light and dark areas, as if waves overlapped. But when scientists try to detect which slit light passes through, everything changes. Light acts like a particle, going through just one slit, and the interference pattern vanishes. So light is both wave and particle. It depends on how you observe it. This discovery changed everything. Realizing light was made of photons, physicists saw the world anew, but found quantization wasn't just for light. All matter, atoms, electrons, you, me, can be described by quantum wave functions, each with its own energy levels. These wave functions determine what's possible and forbidden in the universe. They're like the source code of the physical world. Just as Einstein's relativity predicted black holes and cosmic expansion, quantum mechanics leads to mind-bending consequences. One of the most surprising effects of quantum mechanics is quantum tunneling. Imagine a particle facing a solid barrier it shouldn't be able to cross. In the classical world, it would simply stop. But in quantum scales, it can suddenly appear on the other side as if by magic. It's not magic though, it's physics. This phenomenon explains why today's tiny computer chips sometimes act strangely, with electrons jumping between transistors for no apparent reason. It's not a flaw, it's quantum mechanics at work. Another key concept is quantum fluctuations. At any point in space, energy can appear from nowhere without an obvious cause. This occurs due to the uncertainty principle proposed by Werner Heisenberg in 1927. It states that certain property pairs, like position and velocity, can't be precisely known simultaneously. The more accurately you measure one, the less you know about the other. We might know an electron's speed precisely, but then we'd completely lose track of its location. This knowledge limit isn't due to instruments, but is a fundamental aspect of nature. The universe at its smallest scale deals with probabilities, not certainties. That's why quantum scientists don't say this will happen, but this has an X% chance of happening. It's a world of possibilities, not guarantees. In fact, quantum computers excel at solving these problems with many variables, uncertainties, and simultaneous paths. Luckily for us large creatures in a macro world, these odd effects don't impact our daily lives. They only show up at tiny scales, but they've given us better tools to predict matter and energy, and maybe grasp the universe's birth. The Planck-era scales physicists study are incredibly tiny, with behaviors as strange as you can imagine. We're talking about a time when the universe was just the size of a Planck unit. In this minuscule, super-dense environment, the laws we know simply don't work the same way. In this scenario, there's a central challenge we haven't solved yet: gravity. The universe then was so dense that gravity is crucial, but general relativity explains gravity, while quantum mechanics governs the microscopic world. The problem: these two theories work well separately but don't mesh together. They're like two languages describing the same thing differently, unable to translate between them. This is where one of modern physics' biggest challenges comes in, unifying these opposing views. The name of this ambitious goal: quantum gravity, theoretical physics' holy grail. It could finally reveal what really happened in the universe's first moments. About 150 meters below the France-Switzerland border lies one of humanity's most impressive structures. It's a 27-kilometer circular tunnel, like a giant snake biting its tail, symbolizing the eternal cycle of creation and destruction. This structure is the Large Hadron Collider, or LHC, the world's largest and most powerful particle accelerator. Inside, protons and ions are sped up to near-light speeds, guided by magnetic fields through an almost perfect vacuum tube. These particles then collide with such force that they shatter, and scientists analyze the fragments to understand matter's most basic elements. It's an experiment of epic scale, designed to study the tiniest phenomena in the universe. Indeed, the LHC has given us amazing discoveries, like confirming the Higgs boson's existence. Yet even the mighty LHC can't unlock the secrets of the Planck era. Why not? Because quantum gravity effects only show up at scales far tinier than the collider can reach. To see these effects, we'd need to smash particles to Planck length, requiring energy only a solar system-sized accelerator could generate. So for now, all we can do is theorize. Quantum theory has successfully described three of the four fundamental forces: strong, weak, and electromagnetic. But gravity remains the missing piece. The big problem is that general relativity and quantum mechanics are fundamentally incompatible. Relativity views space-time as continuous and curved, shaped by mass and energy. Quantum theory works with fields in flat space, treating particles as blurred wave functions, not exact points. In quantum mechanics, a particle can exist in multiple positions simultaneously. In relativity, it's a point warping the surrounding space. This problem becomes critical in compact environments like the Planck era. There, these probability clouds or wave functions begin to overlap. At this level, gravity loses meaning as it acts between distinct objects. But what happens when objects merge into an inseparable quantum soup? That's when the equations simply break down. The quest for quantum gravity aims to bridge two vastly different realms, the macro and micro, curved and fuzzy, predictable and probabilistic. Success could finally unveil the universe's first moments. To reconcile general relativity and quantum mechanics, physicists imagined something radical. Perhaps a fundamental particle carries gravity, like photons carry light. This hypothetical particle, the graviton, would be the massless quantum unit of gravity. The challenge is that gravity is incredibly weak compared to other natural forces. This makes gravitons nearly impossible to detect, even with future tech. Faced with this impasse, bolder approaches emerged. One of these is loop quantum gravity, proposing a fascinating idea. Space, rather than continuous, is made of tiny intertwined loops, structures at the Planck length scale. Picture a microscopic fabric, like a carpet woven with invisible threads, where each thread is a fundamental fragment of space-time itself. Another popular proposal among theoretical physicists is string theory, or in its expanded form, M-theory. This approach aims to go further. It seeks not just to unify gravity with the quantum world, but to combine all forces of nature into one coherent framework. It's the dream of a theory of everything. In M-theory, the universe's basic components aren't point particles, but vibrating strings existing in 11 dimensions. Extra dimensions curled up and invisible to us, yet explaining why the universe behaves as it does. If we could grasp these hidden dimensions, we might explain all physical phenomena, from the Big Bang to black holes, from light to time. Clearly, understanding all this requires more than an average human brain can process. Future quantum computers, able to handle overlaps, uncertainties, and multiple paths at once, might advance where our brains still stumble. Currently, physicists worldwide are immersed in this search. Some bet on gravitons, others on loop gravity, and some on superstrings. But so far, none of these hypotheses have provided conclusive evidence. We have many brilliant ideas, but still little proof. Yet, this informed speculation, born from a century of discoveries and countless brilliant minds, lets us imagine the universe's first moment. From this, we can theoretically enter the heart of the Planck era. Princeton University's campus in New Jersey spans vast forests and wetlands, about 50 miles from the U.S. Atlantic coast. Quiet paths between historic buildings and modern labs lead to nearby pine forests and beaches. In the summer of 1955, we can picture famed physicist John Wheeler strolling along Sandy Hook Bay. Watching the waves, Wheeler saw more than just natural beauty. He observed patterns, chaos, and dynamic systems in action. Seeing the foamy surf, he wondered, can we predict this foam's shape, its chaotic bubbles, its fleeting energy? The answer was no. This natural phenomenon was too complex and unpredictable for any precise description. It was there, amid foam and reverie, that an idea began to form. That same year, Wheeler published a groundbreaking theory. At quantum scales, even basic concepts of time, space, and energy might not make sense as we know them. He proposed that smooth, continuous spacetime becomes radically different at microscopic scales, a kind of quantum foam. This foam would consist of random fluctuations, with temporary bubbles of space and time constantly emerging and vanishing. Nothing would be fixed. Everything would be in flux, moving unpredictably. And Wheeler suggested the universe began in this state of quantum chaos. Today, combining findings from general relativity, quantum mechanics, and ongoing attempts at quantum gravity, cosmologists sketch a blurry portrait of the Planck era. The result is a disconcerting yet fascinating image, perhaps the most daring the human mind has ever painted. For an unimaginably tiny fraction of a second, 1/10,000,000th of a trillionth of a trillionth of a trillionth, after the Big Bang, the universe was just 10 circumflex 33 meters wide. That's 100 billion times smaller than a proton. At this absurd scale, space-time as we know it didn't even exist. Time had no meaning. Space was completely compressed. And reality, if we can call it that, was utterly unlike anything we know. According to string theory, at the universe's birth, it wasn't just 3 spatial dimensions and 1 of time, as we see now. It existed in 10 or more dimensions, all compressed into an unimaginable structure, a multi-dimensional hyperspace beyond our comprehension. The best metaphor we have for this is John Wheeler's quantum foam, a bubbling, pulsing, unpredictable space where micro-black holes and wormholes pop in and out of existence constantly. The universe's geometry wasn't fixed. It twisted, collapsed, emerged from nothing, and linked distant regions through unstable temporary passages. And if that wasn't enough, particles like gravitons appeared and vanished spontaneously, defying any notion of cause and effect. In this scenario, there are no fixed physical laws, no logical sequence of events. If anything governs this chaos, it's quantum mechanics' unpredictable behavior. Tunneling, entanglement, and random fluctuations make space twist, blink, and speak like a glitchy simulation about to crash. In practice, space's geometry at this initial moment was an average of all possible geometries simultaneously. Understanding pre-Planck era is like building a family tree where every person ever could be your parent. The possibilities are so vast that logic simply breaks down. Even the greatest theorists hit limits at this point. And experimental physicists, they can't even get close. To simulate Planck-era conditions, we'd need energies so high that even a galaxy-sized collider couldn't handle it. Even if we achieved this by some tech miracle, the result would still be indecipherable. Collisions of gravitons, loops, or strings would create quantum micro-black holes, instantly evaporating into a chaotic particle shower, leaving no recognizable pattern. No useful data, no clear clues. For now, we can only work with the models modern physics provides. And that alone is a monumental achievement. We've probed the universe at tiny scales without physically touching those moments. Maybe by looking back carefully and creatively, analyzing later eras with today's tools, we'll find subtle cosmic fingerprints of what came before time. Thanks for watching. If you enjoyed this, please subscribe, comment, and hit the bell for future videos. That's all for today. See you next time.